Hi there, I'm Paul. Welcome back to the channel, and today we're going to talk about the dead zone. Just a reminder that if you like these videos and you want to see more, please hit the like and subscribe buttons below. Now, onto the dead zone. The dead zone is the distance just below the top of the test piece where it becomes impossible to resolve the back wall echo from the entry surface echo. And typically we find this with 0-degree testing. The signal we see right away on the left-hand side of the screen, even when I'm just holding the probe in the air, of course, that's the initial bang. And when I put the probe on the test piece, that initial bang then combines with the entry surface echo and creates a dead zone in which we can't make reliable readings. Now keep in mind that I'm focusing on single crystal transducers. These are the ones where we transmit and receive with the same crystal. So essentially we can hear ourselves talking. With a dual crystal transducer, we don't really have a dead zone because we're using a separate receive element. Essentially with dualies we can't hear ourselves talk. All we can do is hear the echo part. I'm going to take this 5 megahertz probe and put it on a steel step wedge. In this case, I'm going to use an ERVD, or extended range variable diameter block. It's basically a flat wedge and then 4 different curved wedges built into one block. And it's going to serve us well here because it does have a 1 millimeter step on it. So I'll take the probe and put it on the 5 millimeter step. And you can see here that the dead zone is about 2.5 or 3 millimeters, and it doesn't look like I'm going to be able to resolve the 1 millimeter step at all. So in this case, with this probe on a nice clean steel surface, my dead zone is about 2.5 millimeters. The dead zone will change with frequency, and to demonstrate that, I'm going to use this 10 megahertz pen probe. I'll put this back on the 1 millimeter step, and you can see here I've got no problems resolving 1 millimeter. I could probably take that back to even 0.5 millimeter. And keep in mind that that is about 1/5 what the dead zone was on the other probe. Now that makes sense because a 10 megahertz probe has a much shorter wavelength than a 5 megahertz probe, and for the same number of cycles that means a shorter wave train. And as well, pen probes are typically highly damped, so the wave train is shorter as it is because pen probes are made for resolution, whereas the other probe is made for better penetration. One more thing with the dead zone, do we have it with shear wave transducers? And the answer is not really. Because the probe is mounted to the wedge at an angle, we don't really have any opportunity for direct reflection off of the entry surface. And I can show this to you by just putting the probe down on a block with a little notch cut in the bottom, and you can see that there's not really anything to speak of on the left-hand side of the screen. Those little signals on the left, those are just internal wedge reflections. And besides, with shear wave, we don't really care anyways because we're not interested in things that are directly below the surface. We're interested in things that are hopefully beyond the near zone and may be in fact after the first bounce. The dead zone is really just a question of resolution. How close can I pull the back wall signal in before I cannot resolve it from the entry surface echo? That minimum distance, that's the dead zone. I hope you found this video useful, and thanks for watching.